you might be surprised that he said I am interested in computer science education, but this is my first class in nearly 1 year, because I have not been teaching for last couple of semesters due to some other duties. So it's good to be back in a classroom and teach what I can probably hopefully teach good. And I have big shoes to fill in because Professor Khedkar is my guide, and he is one of the leading authority in India, if not in world, about data flow analysis and related things. So whatever I have here is taught by him. So I hope I do justice to what he has done, and you all enjoy this lecture. Okay, so what have you learned? So can someone summarize? Let's keep it interactive. I have very few slides and I can make it fewer if time is a constraint. Okay, so what all have you covered till now? Day 1 you did about general compilation, different phases of compilation. What did you do on day 2? Program analysis or data flow analysis. What all analysis did you cover? Live variable, available expression, anything else? Please go ahead, go ahead. You said something I knew that was different. See, there is no wrong answer here. Okay, there are no points right now. Maybe there will be in the last exam. I don't know, that I don't control. So you, if you are saying something, please be louder. If you are not louder, I will have to repeat. So at least I should listen. Yes. The available expression and live variable. So you did something which is a forward analysis, available expression, something which is a backward analysis. Okay, live variable. You talked about confluence or meet or something. What was the term used? When there is a branch point or a merge point, how do you combine information? In case of available expression, it is intersection problem. In case of live variable, it is union problem. So there are two more similar problems. So you saw forward intersection, backward union. There is a forward union, backward intersection also. And these are the classic problems. These are like hydrogen atoms when you do in chemistry. Okay. Actual analysis will be much more complex, much more involved. You have to come up with the different kind of ideas, how to represent them, so that they are in finite data structure and so on and so forth. I think he also kind of gave you hint about heap reference analysis, right? Which is kind of my PhD work, and there we had to come up with a very different kind of, in fact, multiple analysis based on these classical analysis. Today we will start with constant propagation. Anyone know what is constant propagation, or what does this term kind of tell you? What do you get from this name? Please be interactive, okay? I have done all this, so I don't need to repeat myself, but you are doing it for the first time. My goal is to excite you. Yes. What does a constant mean? I mean, it's not about compiler, it's in life. What is a constant? Fixed, something that doesn't change. Okay. Propagation, move or forward. Okay, take it around. So constant propagation is an analysis which identifies those variables whose value will not change. Okay. And then it tries to propagate them. So wherever you are using this variable, instead can you use the constant value itself. Okay. So what could be the use of such an analysis? So I want to identify all variables x, please. Let's say I have variable x. Does it have a constant value? For simplicity, let's say throughout the program. It could also be a small region. Okay. And if I do that, if I am able to say, oh, x has value 72 on this line, this line, this line, this line, no matter how you execute the program, what kind of things can you do with such an information? So, constant propagation is an analysis. Finally, all analysis are used for some purpose. Okay, just analysis is not useful. So, what could be a purpose of doing such an analysis? So what is the purpose of available expression analysis? Did you do optimizations based on those analysis? What was the optimization? Dead code elimination, I don't think so. Before that there is something, I mean dead code of course happens later. Common sub-expression elimination, CSE. What about live variable? Live variable is where you do dead assignment or dead code elimination. Okay. So again, see, you don't have to mug up things. You think about it. If a variable is not live, then it is dead. So you want to remove any assignments or remove that variable. Similarly, now you have found out a variable is a constant. I mean, its value is always a constant. Okay. So what can you do in such cases? Anything that comes to your mind. As I said, this is not a exam. This is not KBC. You are not going to lose 50 lakh rupees. Okay, you are not even going to get it. So why not try? You write programs. So what can you do if you figure out, oh, this variable is always going to have the same value throughout the program? You can replace it by the value. Okay. So and then delete the variable. So again, some kind of dead code elimination. Now my question is, why not start with the value itself? Why do you want to have variable x in the program, then painstakingly do constant propagation, then remove it? That's, I won't take too much time, but that is like good programming practice to give descriptive names to variables. Okay, maybe you have a variable called pi in your program rather than putting 3.14 everywhere in the program, because tomorrow it's not as if pi value is going to change, but you might want more precision. So you might go with 3.14159. Okay, you might want to do that because probably your application requires more precision. Now you have to change this value at 25 different places. Instead, if you are using a variable, you can just change it at one place and you are done with it. Okay, but then your program runs slow because anytime you have to read a variable, it has to load from memory, right? So it can create slowdown. Memory is always slow, cache is limited, all those things. I think those are architecture thing, but still. So at execution time, you don't want that overhead of reading a variable. So compiler can play smart. It can do what you are kind of not allowed to do because of good programming practice. So it can replace all pi by 3.14 or 3.14159, or maybe if you are not interested in floating point, then 22 by 7. So anything like that can be done. Okay. So this is a data flow analysis which we will discuss. We'll continue from what we have done with respect to identifying constant expressions in a program. So not necessarily a variable is a constant, it could be an expression also. You might have x times y or x plus y, and you figure out both x and y are constant, in which case you can evaluate this value x plus y. Let's say x is 72, y is 13, you evaluate it 85, and now z is equal to x plus y, z will be identified as a constant. Okay, so you are saving a runtime calculation. Again, it sounds like one calculation, but it can be in a loop or it can be loaded from some memory, so it can save you a lot of effort. Then we will identify some similarities and some differences with the bit vector data flow. So ideally we do all four, but here since you have done two of them already, we'll try to identify those, and we'll look at some other properties of constant propagation. Okay. So let's call it CP. CP is the problem of replacing expressions that will evaluate to some constant value C every time they are executed. Okay. So note that this is very important. Whether you execute this program during day, during night, you execute it in Kanpur, in Chennai, you execute it once, you execute it 1000 times, this expression is going to evaluate to value C. Okay. So what could be the domain? Have you done all these exercise with the available expression or live variable? What is the domain? What kind of values a program can take, or your what kind of interesting values these expression can take? What can they take in case of available expression? An expression of interest. What could be the data flow values there? What could be the values of interest? It's called bit vector for some reason. It's binary. Each expression can either be available or not available. True, false, 0, 1, whatever you want to call it. Am I right? See, please stop me if something is not clear, even if you missed something yesterday. What do you think can the values be here? So my interest is expressions. And I have to check whether they can evaluate to a constant value or not. So what can I get? What values should I be able to see? As I said, in live variable, I can see live, dead. In available expression, I can see available, not available. In reaching definition, I see D1, D2 that you have not done. That definition D1 reaches, definition D2 reaches. What do you think will happen in? I have an expression y star z, y plus z. What values can you see? Constant, non-constant, good, first attempt. Okay. But saying this value is constant, is it good enough? The reason is I get y plus z is constant. Again, I am just going little ahead, but to give an intuition. On one path, I get y plus z is constant along other path. Now I have at the merge point, if then else, I am merging. Is it good enough to say x plus y is constant on left branch, x plus y is constant on right branch, to merge them together? What if they are two different constants? What should happen at merge point? I will discover that the value is no longer a constant. Is it making sense? All this I will do with the kind of equations as well as drawings and all. But intuitively, x plus y I discover to be 32 on left branch and 52 on right branch. So where they merge, where my program if then else combine, can I say x plus y is a constant? No. So which means I need more than just true or false. I need repeat actual values. I need actual values also. Sorry, louder please. We do need for every expression, but let's say we are focusing on a simple one expression at a time. It could be x, it could be y. Variables are also expressions finally, right? So we need to store values for x, for y, maybe for x plus y, z, everything. Okay. So very good point, because that's what will come next. So what is the domain you think? I really need not worry about x plus y, because if I know x, I know y, I can always compute x plus y. So for every variable, I need to keep track of every possible value that variable can take. Okay. And what is every possible value? How do you know that? If you are writing a program, what tells you what kind of values variable x will take? Type. Very nice. So let me go ahead. For a variable v of type tau, all possible constants of type tau. This is my domain. So if you have 20 different types in your or at least you want to analyze variables of 20 different types, you have to find out what are different constants possible in those 20 different types, and in a way for every variable, every of that type, those values. So if I am talking about integer, I have to worry about minus infinity to plus infinity. If it is a boolean, I have to worry about true false. If it is a character, I have to go from 0 to 255 or whatever character set you are using, like that. Does it make sense? So you can see domain is very big in this case. In available expression, it was true and false in some sense, or a mapping from something to true and false. Here it's a much bigger thing. Did you talk about semi-lattice? No, so we'll kind of skip that. But top and bot, did you talk about? Or optimal value, or okay. So meet you must have talked about. Join point, what happens when? So available expression, how did you combine information? Yeah? So intersection, okay. So that is also called meet. Okay, meet is a general name across all. So meet is intersection for available expression, union for live variable. Okay. Basically, if information is coming along two different paths, how do you combine them at the joining point? So So this is if something, some branch, let's say x star y is available and x star y is not available. This is not assignment, this is just available or not available. Last, can you see this? Can you read this? Should I write bigger? So what will be the information when these two paths merge? What can I say about x star y here? Is it available? Is it not? On one path it is available, on one path it is not. So this is not available. I can't say it is available here. So confluence operator you said is intersection. Confluence, meet, these are the names for this. Okay. What can you say about constants? X is some value C1 here, X is some value C2 here. What can you say about X here? This is intuition, maths, no, nothing computer science, nothing very difficult. What can you say about X in terms of its constantness? Can you see the whiteboard, the front seat, or is it getting, you see it, right? So X, what can you say about X here? I am saying X is constant 1 here, X is constant 2 here. What can I say when this is a program executing? Okay, what can you say about X? Is it constant or not? Under any circumstances. What if C1 and C2 are equal? So then X is a constant. If they are different, or on one path I have X is not a constant. Somehow figured out, not a constant. So already on this path X is not a constant, then also it will be not a constant. Okay, so like that. Did you talk about initialization of data flow values, boundary conditions, entry? I doubt that you did not talk about it. You must have talked about it. Without that you can't do available expression. Okay. So what is the most optimistic value? Have you talked about this? For example, available expression, optimistic value is everything is available, or a given expression is available. You start with that assumption, your analysis, right? Did you talk about this? No? If you say no, I will not believe you, because I know Professor Khedkar and I have been taught by him. Okay, without this you can't do analysis. So what is top? Did he talk about properties of top? Oh, not here. The given a value D, top meet D always. Or union in case of available expression. Okay. Okay. So what was the so I want to discover constants in my program. I have analyzed one path. I am still yet to analyze the other path. I have not yet analyzed this path. Okay. So how do I combine these two path information? So generally because data flow analysis is not forced by your the order of program. I can process this block, then I can process this block, then I process this. So this is the order: first, second, third. Okay. So for such reason we always initialize data flow analysis with a optimal value, optimistic value, not optimistic value, so that it does not change the behavior of things which we have discovered. Okay. So what I say, if I have not processed this block, I will say X has I'm just putting top right now, some value top here, such that when I merge these two values, this is something I have discovered, it is constant. This is something I have to discover in future. Okay. So since I have not done it, I will still be optimistic. I will assume that maybe this is going to be constant, so I will be lucky. So that the combination will still give me X has value C1. Okay. So top I have to choose boundary information. That's the boundary information because initialization information, not really boundary, initialization information. Okay, so this is the boundary information. Okay, BI, let me call it BI. Okay, so this T means boundary information, something which you start with. You have to start somewhere. Okay, and the property is it does not change the other person if you are combining it with other person. There is a nemesis of this person. What did he call that? Bot. Did he use bot? Okay, so worst case, pessimistic information. This is will be shown as bot. Okay, this is something which kind of always influences the other guy. So look at this. So unlike available expression or live variable, because you only have true false values, here you have so many values which are all of the same stature. You need some special values. One is not a constant, okay, which means the value is changing. Okay, one is undefined. So not a constant says you have already got enough information about a variable to say that its value is not a constant. You found 52 on one path, 32 on another path, you combine them, at combination you can't get a proper constant. Okay, sometimes what happens, you have a definition for which you cannot figure out what it is. It could be reading from this user. You are asking user to give a value. Now you don't know what user is going to give. Okay, you do a scanf or you do a input. So you don't know what is the value. So in such cases also you will say, oh, x is a non-constant. Okay, you are assigned an uninterpreted value. Basically you say x equal to some foo, some function xyz. Now at that point you don't know what xyz is going to return. Is it going to be a constant or not? In such cases also you would say that, oh, I don't know, it's not a constant. Some complex value. Okay. Undef is you have not yet seen enough about x. You have not explored certain paths. So that is undef. No definition of the variable is seen yet. Nothing is known. There is a difference between not a constant and undef. Are you able to get that? This is very, very important. Okay. Yes. So not a constant is when you have seen enough about a variable to say that, oh, its value cannot be a constant. Okay. Now why can that happen? Maybe you are reading an input from user, you are reading value from a file, you are reading value on a network where you don't have any control, any value can come, or you have found two different constant values which are merging at a point. On one path x is 5, on another path x is 7, and you are talking about that merge point, what is the value of x. See, okay, so you know for sure that x is not going to be a constant from this point onward. Okay, so not a constant is where you have confidence to say that value is not going to be a constant, or it could be some very complex function. Okay, so which is again not interpretable for your analysis. Analysis can ignore. It can be a library function. You don't know what it is going to produce, right? On the other hand, undef is because see, I don't process this program in order. I can pick any block to process. So I picked up a block and suddenly I see it says so suppose my program is like this. If y is greater than 5, x equal to 20, z equal to 40, something random program, and then I have w equal to 2 times x. Okay, I want to ask what is, so maybe I started with this block. Data flow analysis does not force you to go in this order. You can pick any block and process. Now you picked up this block, you asked is x a constant or not, but then you have not yet seen anything about x yet. This is the first block you are processing. At this point you will not say x is not a constant, because what if x is a constant on both paths later? Okay, so then you are losing out on opportunities to optimize or to discover information. Okay, So at this point you will say, oh, I don't know much about x. I can't say x is 20, I can't say x is 40, I can't say x is 90 because I really don't know anything, but I am just assuming x is a constant. So I use a dummy value which is undef. Undef is a dummy value. Okay, it just says that, oh, I don't know yet, but please treat me as a constant. Later we will fix, if we find enough, I will mark you as not a constant, or if you are really a constant, I will mark you as 20. Okay, is this point clear? This also happens in available expression, this also happens in live variable. Only thing is there you don't need a special value, you can always use 0 or 1, okay, one of them acts as undef. Here, because this is a different from any other constant, you don't have just 1 or 2 values, you have infinitely many values, you have to add it separately. It's not a program constant, it's a dummy constant that you have introduced for doing better analysis, okay. So just to reiterate, NAC is too many definitions. When I say too many, different definitions, different valued definitions have been seen for a variable to declare V is not a constant. We are declaring that, oh, V is not a constant. Undef is too few definitions. You have not seen enough to declare anything about V, to say anything with confidence about V. Okay. Yes.
What if one of the branch contains
I will repeat, you can go ahead.
What if one of the branch contains an expression, for example, x is an expression which evaluates to x, and that expression is dependent on some other variables?
So you are saying on one path I have x equal to some expression y plus z, is that okay? Or
Yeah.
you want y, okay?
Right.
And you still have not known about y and z, okay? Now there are two things. Have you, okay, so let me just make it a slightly complete program. What happens on the other path, or the other path is not relevant?
Not relevant.
Not relevant. What about, what do you know about y and z?
Nothing.
Nothing.
Nothing at all.
Okay. So basically y is also undef and z is also undef. Is your question?
Yeah.
Everybody is able to understand it? I picked up a block. I saw it contains x equal to y plus z, but this block happened to be such that I have not yet seen y, I have not yet seen z. Okay. So I have undef plus undef in some sense. We'll come to that, how to resolve such. So you have to now define semantics of plus, minus, star, what happens when they see undef. We'll come to that in a few moments. Okay. So, but just to give short answer, because this is what I am saying, too few definitions seen. You are seeing a definition of x, but internally you have seen too few things about y and z. So you are saying, oh, I have not seen enough about x. So x will also become undef. Later you discover y is a constant, z is a constant, x will automatically update to constant, or y is not a constant, x will also become not a constant. Okay. So what I am saying, undef is a optimistic choice, that okay, I am treating you as a constant, I don't know anything about you, but later sometime I will have seen the whole program and I will come back and fix you. NAC says, oh, now you are a gone case, I have already figured out you cannot be a constant, because after a certain path you have some value and another path you have some different value. In fact, even difficult question is, what if y is undef and z is not a constant? What if both of them are not a constant? So we have to worry about all this combination. Yes, very good. Questions? Yes. If you understand all this discussion, my rest of the slides will be just, we have to just pass through them. Yes.
Yeah, like while writing a program, we are saying if we have seen too many definitions or too few definitions.
Not writing the program. Program you are writing.
While analyzing the program. So
yes.
how do we decide like what is the too many number of definition and what is too
Right. So as I said, when you initially, this undef is also boundary information. Okay. So when you start, you put every variable is undef. That's how you start. No matter where you are, you assume every variable is mapped to undef. because initially you have seen too few definitions anyway. And then as you process the program, you fix things. You know, data flow analysis goes through multiple iterations of the program. That part at least must have been taught. Okay. So every iteration you will fix some definitions, you will keep doing that till all the definitions are fixed. So every definition, finally no definition will have undef as long as it is there in the program. It will either be NAC or a proper constant. Okay. Yes, this is good, we will do that. In fact, we will solve some simple problems. These are two requirements of our confluence or meet or intersection union kind of operator, that top meet x should be x and bottom meet x should be bottom. So what does it say in this case? If I have declared a variable to be undef on one path and constant on another path, their confluence I will still continue to maintain that variable is constant. Why? Later this path can discover it to be the same constant, in which case my decision will be validated. This path might discover it to be a not constant, in which case at that point my confluence will declare it to be not constant. So it can be fixed. Once I mark something to be not constant, I cannot go back to mark it as a constant. Non-constant can never become constant. Undef can become constant when you have discovered enough. So undef can become constant, constant can become not a constant. We can't go in the reverse direction. Again, these are all have very good mathematical background. I think that probably we are not able to cover due to shortage of time. This is a whole semester course we are putting in 1 or 2 days. So undef, when it meets with C, it becomes C. It behaves like a constant, but something discovered as not a constant on one path, when it meets with a constant, you still have to say it's not a constant. X cannot be a constant because this path it will anyway remain not to be a constant. Okay. Now C1 and C2, on one path you have discovered constant 1, on another path when you have discovered constant 2. Now from this point onward, if they are different, then it is NAC, but if the both of them are same, then it continues to be the same constant. Okay, is this idea clear? You are given a point, depending on incoming information you are declaring whether at that point variable is going to be having a constant value or not. Okay. Now semi-lattice you have not done, so I am going to ignore it, but this is the kind of information. You have undef, which is very optimistic value, which is very good for your optimization. If some variable remains undef throughout the program, you can just delete it. It's not useful. If some variable gets one of these values, you can replace it by the value and then delete it. If some variable becomes NAC, then you can't do anything, you are lost. You have to keep that variable as it is, because in different runs of the program, you will get different values. Okay. So this is something called lattice. It's kind of an ordering on the values. In case of available expression, lattice was very simple, true and false, two values only. Here it's very fat or width wise, very wide lattice. Okay. And note that this is only for one variable. Actually it will be for every variable you have similar lattice, and then you have to combine them, lot of mathematics there. But you really don't have to do all this in your analysis, everything is done implicitly. Okay, so I will skip this slide. Now we come to the question that you had asked. Okay. So in case of available expression, you are having this flow for a statement or a basic block. You talked about that, gen and kill. That part was talked about, right? We have to define gen and kill for our constant propagation also. Now here plus does not necessarily mean addition. Plus is any operation. It could be multiply, it could be negation, negative, or it could be some function also. It is just a placeholder. Okay. So suppose I get a statement x equal to c. And again, just to remind you, how does data flow work? First thing, is it a forward problem or a backward problem? Intuitively, if you are trying to discover constants, will you go from start to end or end to start? Is it like available expression or live variable? Live variable. So why? You want to figure out whether x is a constant or not. Given a statement, will you know after the statement or before the statement that x is a constant? After the statement. So you have to go in the execution direction, in the direction of execution, so forward. So this is a forward, okay. Now you are given this statement, x equal to c. This is your block, okay, simple. What can you say about data that you will generate? Immediately after this statement, you can be very sure that x is going to be a constant. So the information you generate is x is a constant, okay. And what will you kill? Basically any other mapping of x. So here you will say, sorry, not just constant, you will say x is a constant c. And any other mapping, x is a constant 5, x is a constant 27, that will get killed. Okay, even x is a not a constant will get killed. Before it, x could not be a constant, it might have multiple values, but after this statement, you are very sure x is a constant. Okay. What about the second statement? Undef. You can clearly say x is undef.
Because we don't know what is there and why it is.
So can you make some kind of case statement, case analysis? Okay, very good. So first step, very nice. So in this case again there is something slightly different from other analysis. In fact, it was there in live variable. Constantness of x depends on constantness of y and z. You have to know what is x, what is y, what is z to figure out whether x is a constant or not. So exactly as he said, if y is constant 1 and z is constant 2, where? Before the statement. Okay, in and out, have you talked about it? In means entry of the statement, out means after the statement, before and after. So if my in information contains y is constant, z is constant, then x is going to be the evaluation of this expression constant, assuming this expression also evaluates to constant. Okay, so x becomes c1 plus c2. And again, as I said, it can be c1 multiplied by c2, it could be c1 to the power c2, plus is just a placeholder. Okay. What are the other cases? Maybe y is not a constant. Okay. Then no matter what z is, I have to say x is also not a constant. What if z is not a constant? Again, so what can y be in this step? Y can only be undef, because y is not a constant c1, y is not, actually there's slight more combination, but yes. So it does not matter, z if not a constant, then your expression is not a constant. Otherwise, y is not a constant, z is not a constant, so they are NAC not even not a constant, so undef. So x is undef. Okay. So these are the kind of analysis you have to do on operator. Again, this analysis might slightly differ if you have an operator. You can even do things which are slightly more interesting. What if my expression is x equal to y times z? I am giving this as a challenge, and my in information contains y maps to 0 and z maps to, I am not putting anything here. Can you say x is mapped to a constant 0? Yes or no? Okay. So of course you know mathematics, you know multiplication, you can say it, but you have to be little careful when you try to prove correctness of your optimization or analysis or optimization. Again, this is something involved mathematics, we won't do it much, but what I am trying to say is, depending on your operation, your flow function, this is called flow function if you remember, your flow function can differ. Okay, I am giving you a very generic kind of flow function, but depending on your analysis, your optimization and your operation, flow function can be little different. Okay, you are just learning these techniques because tomorrow you don't have to do constant propagation, people have already implemented it. You will come up with your own analysis, your own optimization. Remember these kind of things, that what kind of opportunities of optimization you search. If you blindly follow this, you will mark X, let's say this is NAC, you will blindly mark X as NAC. But maybe because of the semantics of multiplication, I can always know, no matter what Z is, because Y is constant 0, X is going to be constant 0, okay. And finally, as I said, X is a complex expression. You can't handle it for whatever reason. It could be a print, sorry, not print, it could be a scanf, it could be an input, which means you will always define it to be not a constant. Okay, is this thing clear? Did you talk about monotonicity of flow functions? Sir mentioned. Right. So what happens again, see, if you are doing an analysis, you do one pass, you go from 0 to 1. You do second pass, you go back from 1 to 0. Third pass, you go from 0 to 1. So then such an analysis will never terminate. Okay, will keep on going, oscillating between 0, 1, 0, 1. Okay, so there is a property of these flow functions which guarantee that your data flow analysis terminates. Once you guarantee that property, it will guarantee that it does not oscillate. That is called monotonicity. So this function, we can prove that it is monotonic, which means if you do constant propagation analysis, it will terminate after a few iterations. That is a guarantee. How do you prove this function is monotonic? I don't know if you did it for others, but it is slightly involved. It requires case analysis on this transfer function f, whatever we talked about. This is our f, whole thing. Okay. You have to know that in the lattice, NAC has less information than C, and C has less information than undef. C can be any constant. Okay. So there are three different cases: x equal to C, x equal to y1 plus y2, and x equal to some complex expression. X equal to C has a constant transfer function. So constant functions are always monotone. Monotonicity is if you change x in one direction, the fx also changes in the consistent direction. Okay, it does not oscillate. This also is a constant function. Constant functions are always monotonic. They are always in one direction. Okay, they are not oscillating. What about the third case? Third case is little bit more involved. You have to fix one variable to one of the values and change other variable from one direction to other, and show that result also changes in the same direction. So confirm that x does not increase, it always goes down. Okay. So do this for all z choices. So first pick z to be ndef, then pick z to be C2, then pick z to be NAC, then you do y as ndef, C1, NAC. So basically you create a matrix and show that this matrix does not increase. So let's do it. I think that's an exercise. Even if you have not done for available expression, this is a good exercise for constant propagation. So basically I have to create a table which will compute transfer function for y plus z, or flow function for y plus z. On one side I will put y, on the other side I will put z, and each value here is going to be the value of y plus z. So all of you can create this table, 3 by 3 matrix. It will become 4 by 4 because we are putting x, y, z values also. So y is undef, C1 nec, z is undef, C2 nec. Okay. So what will be the value here? This is the simplest one. So let me fill it. This value is going to be C1 plus C2. This is actually value of x, mapping to x, which is a constant value. Okay. If y is C1, z is C2, value will be C1 plus C2. What about this value? We have looked at, let me go back here. Yes, this will be NAC. So it's easy, all of these will be NAC. Same here, all of these, because any one of them is NAC, you are NAC. Okay, what about this one? Undef. Undef meets undef plus C2. C2. So this is something you have to define for all different operations, as I said earlier also. Okay. If you want 0 to be treated separately, you have to put a special entry for 0 here, a special entry for 0 here, and create this whole table. Okay. Similarly, here it will be C1. Now look at any row. When we go from NAC to undef, this should also go in similar direction, or if we go from undef to NAC. Okay. So you can see that in this row, undef is greater than C2, it is greater than NAC. This is also greater. Okay. So if I move in this direction, I am still greater. X is changing like this, Y is also, or Z is changing like that, X is also changing like that. What about here? So this is like equal, they are at the same height, this is greater. Okay, this one they are similar. Same here, undef. So this is also like that. You will never switch. Okay. So these are constant functions. This is kind of constant. This is also going in that direction. That's how we picked it up. It is an assumption. Okay, this is as I said, this is a dummy constant that you have put in, which we are defining it to be in a way better than all other constants. Why it is better? Because if you merge C1 and C2, you get not a constant. But when you merge undef and C2, you still get C2. So we are treating it as a, again, it's not really a constant. Undef, what I am saying, it's a dummy constant. It is not a program constant. It can never occur in program. It is there to make our analysis easier. Yes. So, okay, what happens? Let's leave it. So, yeah, go ahead. I will repeat.
Like we are assuming it as undef doing analysis, but what if it is actually a variable and it was never a constant? X is equal to y and y was never a constant, but it was another variable to begin with.
Okay, so very good question. She is saying initially we assumed x is undef, but in the program x is y plus 5, let's say, and y is not a constant. Okay, so one thing, initially x is undef, but today or tomorrow you will come across this statement x equal to y plus 5 in your program, and your data flow analysis has to analyze that statement, at which point x, so y plus 5 will fall into this column, this is 5. So you will discover y plus 5 to be not a constant. 5 is a constant, so this is 5. So z is 5 and y is not a constant. So when you process this statement, this will be the mapping for x. See, this is what you are updating, x, this is x mapping. Initially you assumed it is undef, but whenever you process y plus 5, multiple things can happen. So y plus 5 is this line, y plus c2. Okay, so maybe y is undef, in which case you will say x is c2. Maybe y is some c1, in which case you will say x is c1 plus c2. Or maybe y is not a constant, as has discovered, so you will say x is also not a constant. So this, remember, data flow analysis does not say you stop once you have done something. You have to keep doing it till you reach a fixed point, till you reach that there is no further change possible. And you have to analyze every statement. It does not matter in which order. So someday you will come to this statement, at which point you will mark x as not a constant. Okay. Now x is marked not a constant. Now this is where monotonicity comes into picture. Once x is marked not a constant, it will not change. Okay, monotonicity of flow functions will guarantee that x will not no longer change. X can never become constant next time. X can never become undef next time. Okay, so there are these guarantees which are given you have a no, somewhere else it can become. At that point it will not. So later if you have x equal to 72, of course there it will be discovered as constant. So okay, so all this is with respect to a given program point, given region. It's not, because x can be non-constant here but constant there. In function 1 it can be constant, function 2 it can be non-constant. So these are data flow analysis values are point specific values. Okay, given a program point you say something. At that point it has to be, yes, it has to be monotonic, it can be on either direction. Okay, again I don't want to go into mathematics, that's why I am saying set size can grow or shrink. It can go from NAC to C2, or it can go for NAC to NDEF, or can go from NDEF to NEC. It can remain same, but it cannot change its direction. So it can be like this, or it can be like this. Okay, or it can be like this. It cannot be like this. A function's graph cannot be like this, or cannot be like this. That half the time it is decreasing at a given program point. Okay, so it will take yeah, because we are doing it little fast. So what it says is, once you have declared x as not a constant at a point, at that point you can never discover it to be a constant again. Okay. So why don't you solve this intuitively? I mean, no matter, because again we don't want to do very mathematical thing. This is a program, this is some if condition. We have two different paths. Okay, tell me what is x, y, z after B3 at the end of the program. I am giving you a specific point. At the end of B3, what are the mappings for x, y, z? We have to discover constants. Okay. And I am saying don't worry about data flow analysis. Do it in any way, intuitively, non-intuitively. If you know some other method, do it that way. Just tell me what is your expectation about values of x, y, z in terms of undef. Undef to nahi rahega finally. Not a constant and some constant values. Or you can do it at every program point. Let's do it at end of B1, end of B2 and end of B3. So out. So what is the situation at out of B1? X will be constant 2. Out of B2, x will be constant 3, and out of B3 x will be not a constant, clearly, because it sometimes it is 2, sometimes it is 3, depending on how you execute the program. Okay. What about y? What can you say about z? Okay, so yeah, we'll look at this. It is undef. You have not seen any definition. Undef. What about this place? Not a constant? or constant 5? Constant 5, okay. So what is the correct answer? Yeah? So as I said, in this class there is no correct answer, there is no wrong answer. It depends on your analysis. How do you do that? If you do data flow analysis, the way we have talked about, or I mean the way we are not able to talk about due to lack of time, it will come out to be NAC. Okay. But if you have, there are different kind of analysis. So you can do path based analysis. You enumerate all paths in your program. So path based analysis, what it will say, there are two paths in the program. And this is something Professor Khedkar has talked about, at least kind of given hints to. There are just two paths in this program. Okay. What path based analysis will do, it will compute values along this path. It will compute values along this path. And then only at the end of path it will merge the values. Okay. Got it? So rather than combining values at in point, why did you get x as NAC? Because you said x is 2 here, x is 3 here. At in of B3, x will be NAC. At in of B3, y will be NAC. And then you used our table, NAC plus NAC is NAC. Okay. This is block based analysis. Path based analysis is saying, okay, I take this path, z is, x is 2, y is 3, z is 5. I will take this path, x is 3, y is 2, z is 5. So along this path z is 5, along that path z is 5, I combine the information, z is constant 5. So path based analysis, this is the correct answer, this is the wrong answer. Block based analysis, this is the correct answer. In fact, I should not say wrong answer, this is a non-optimal answer, and this is the kind of, so this is block or data flow analysis does block based analysis. Path based analysis gives you, so why are we so much insistent on data flow analysis, not path based analysis? I mean this, it always gives better answer, and again mathematically you can prove that. I have slides but I am not going to touch them, that path based analysis will always be better than block based analysis. Okay, in they can be same, like in available expression they will be the same, but in general, okay, there will be large, in fact there are unbounded number of paths, not exponential, nothing. In a while loop you don't know the condition when it is going to terminate, so you have to keep doing it. It can run for 10 times, 1000 times, it can be an infinite while loop. So yes, so the paths are not tractable, intractable problem. So block based analysis is an approximation. So as I said, this will always be a safe approximation. What it means, you will lose out on opportunities to optimize. If I am not able to say z is constant 5, I will not be able to delete it and replace by 5, but my program will still run correctly. On the other hand, if x is not a constant and I declare it to be constant 5, not here but in some other program, then my program will go wrong, because z actually could have been 27 and I am treating it as 5. Okay, so generally data flow analysis, block based analysis will give you a safe but approximate answer. Path based analysis will give a better answer. Okay, but path based analysis are not feasible to do. There is guarantee that path based analysis will always be approximated by block based analysis. Okay, but there are examples where the two will give you same answer, like available expression, live variable, the 4-bit vector analysis. So those analyses are called distributive analysis. It does not matter whether you merge information here or here. Those are called distributive. Constant propagation is non-distributive. You cannot, and those values are called meet over path. First you do all the paths and then take a meet or combine the information. This is maximum fixed point where you do iterative analysis and get a standard thing. Okay. So in this case, of course, not a constant is an approximate value, so it's kind of a lesser value than MOP value. Here less does not mean small or big, it just means it gives you less opportunities for optimization. Okay. So here is, we stop with non-distributivity. There are other cases which we'll see when we do later SSA based analysis. Okay. Any questions? 1 hour is over. One slide, set of slides. Okay. And you can think about how they compare to available expression live variable. Yes.
What if a variable takes a value which is in an array? Let us say we know variable takes some constant values, but there are multiple constant values.
So again, let's make it a concrete example where you want to say x equal to some array.
X equals to some array of values.
Oh, what is the type of x?
We know that x takes constant values, but it can be multiple constants.
Can be one of these.
Yeah.
So that is a non-constant. Again, classical data flow analysis will treat it as a not a constant value, because sometimes it can be 5, sometimes it can be 7 at that same point, right? Yes. Now if you have some different optimization which you can do based on, oh, the values are limited, then you have to define your own analysis. The classical, this won't be able to catch it. Okay. On the other hand, if you have something like x equal to some array at index I, okay. So there are two ways. One is you treat array of I as a complex expression and say, oh, I can't handle it, so I will treat x as not a constant. So even though in program actually that whole array might be containing the same value, okay, but still you will treat it as not a constant. Or the second is that you write another analysis to analyze this array I, to declare that array I can only have a constant value at this point. So you have to extend the analysis. Classical one will not be able to do it. Okay. So such thing we call uninterpreted expression. We are not even trying to see what they are. If you can improve uninterpreted functions, then your analysis will improve. Its precision will increase. Yes. Anything else? Very silent crowd here.
Sir,
Are things clear? And think intuitively. Yes, please. Somebody said.
sir, why are we using greater than or equal to sign when we are ordering NSE, C and UNDEF?
Oh, because sometimes they can give same information. Okay, it is a possibility. Here, this one. Okay, so slight mathematics there. This is lattice partial order, so I don't want to go into that. It's like it can have same information or more information. Yes.
Sir, what happens if we get error when we the type of x and y are different and we do addition operation?
All right. Okay, very good question. What if this is an program error, compile time error, runtime error, things like that? It could be y divided by z, and z turns out to be 0 at runtime. Okay. So yes. So once again, the idea is either you do an analysis to catch this error, or you assume program is error free. Okay. The guarantees hold only if your program runs properly. Okay. So if you are saying y is a integer and z is a string, and you are trying to add them, and your program does not allow that, language does not allow that, then someone has to catch it. Data flow analysis will not catch it. Data flow analysis will assume that program is correct. Okay. Or you have to have a separate analysis. So data flow analysis is very focused entity. If you are doing constant propagation, it will only do constant propagation. It will not even delete it. Even if it has found dead elimination, we'll actually do one of the analysis, SSA based analysis, which mixes discovery of dead branches with constant discovery. Okay, that is very interesting, very powerful analysis which we will do. But in general, data flow analysis are popular because they do one task very diligently, but they don't look left and right. They will not try to change program structure. They will not try to discover additional information. They will not try to find errors or anything, unless the the goal of analysis is to discover error. Okay. So for example, you can have a divide by zero analysis, which will be like constant propagation, but it will be only interested in zero in the denominator. Please.
Sir, you told that if expressions remain undef, we eliminate them, right?
Either they are not there or we can eliminate them.
Okay. Then why should we start considering the starting point is undef, not NAC? Because considering it as NAC would be the most safest option, right?
Yes. So then you can't do any optimization. That's the reason.
Okay.
See, I can assume every expression in my program is non-constant. Then I don't even have to do anything. I just run the program. I can assume there is no available expression in my program. I can't do CSE.
Like, can't we do that? First, we consider expressions as NAC, and later throughout the program, we.
So again, once again, the challenge is proving correctness of your program, that it doesn't. How do you prove that your analysis will terminate? Because you will go from NAC back to constant, then back to undef, then come back to NAC at the same point. So it will keep oscillating. What stops it from going from NAC to constant, coming back to NAC, and then going back again to constant, coming back? Here the way we are treating it, it will only move in one direction. Okay, this is not a wrong thing to do. I'm just saying that once you do things in data flow style, you don't have to prove lot of properties. They are guaranteed by the underlying framework, mathematical framework. Okay, so it is like saying that you find you know how to multiply two numbers. You don't have to prove to your friend that this is a correct way of multiplication. You find some very fast way of multiplication. That's a Booth multiplication. Now you have to prove to your friend that this multiplication works. It is your responsibility. On the other hand, if you use classical multiplication, you can just say, oh, wo to maths ki book mein hai, we are reading it, and that we don't have to prove it. Same thing here. What we are doing, lot of proofs we don't have to do, because they have been done once and for all. If you try to do it differently, like I will show in SSA, we will do things differently, and then there are full paper about proving that that kind of analysis is correct. That is not a traditional data flow analysis. Okay. So you get it, right? There is a path from Kanpur to Chennai using flight and all. It is a well tested path. I take it, I don't have to worry about looking at Google Maps whether I am going on the right path or not. On the other hand, if I take my own car and I try to explore through some jungles and all, I will have to consistently validate that, oh, I am on the right path, I am going towards Chennai or not. Okay, it should not happen that I go towards till Jhansi, then go towards Delhi, then again come towards Bhopal, then go towards Kanpur, and then I will never be able to reach here. So I will have to keep track of my progress somehow. Okay, anytime I am going back, I will have to correct my course. Same here. If you do data flow, that's like taking a flight which is well tested, well designed. If you do it on your own way, it's like taking your own car. Now it's up to you how you prove that you are going to reach. Okay, and then there are other things like petrol consumption and all other things you'll have to show. So time of the analysis, timing, correctness, all this will be your responsibility. In this way, we just have to prove correctness. Termination is guaranteed. Okay. Good question, because whenever you are designing new analysis, you also have to decide whether you have to do data flow analysis or not. In fact, introducing a 0 times x is 0 makes your analysis non-monotonic. Okay, so then you have to prove correctness in some other way. It's not wrong, because we all know that it is not wrong, but it might feel, you won't be able to prove it correct. Okay, so what is it? Do we have a break or something? I don't know. How is this? It's 10:15. 10:30. Okay, so then I will start the next topic. Just introduce. So, when Professor Khedkar introduced data flow analysis, he must have talked about 3 address code. What is the 3 address code? three addresses basically, two operators, two operands, one result, and generally one operation. This is the maximum. It can have fewer. Okay, what is the advantage of such a representation? No, no, they are two different things, not better version. It's a linear version of AST. Okay, linearized representation. Okay, AST is something different. Okay, but what is the advantage from analysis perspective? It's very structured. You don't have to worry about whether there will be 5 arguments, whether there will be 2 operations or 3 operations. Okay, each statement in itself is very simple. But then what is the disadvantage? More number of operations or statements. Okay. Secondly, it is difficult to see the extent of effect. If I have x equal to y1 plus y2, then there will be t1 equal to something, t2 equal to something, somewhere down the line x will be used. So many times it becomes difficult to see how x is affecting rest of the program. Okay. Then you have to carry all this information, create, if you try to find def use, which you have not done, you did not do reaching definition. So you have to find usage of each definition, so all those things. So it becomes very dense kind of graph. So there was a very nice proposal again in 1980s by a group from IBM called SSA form. So in this slides we look at SSA form, how to construct it and what are its properties, what are some applications. Okay. So this was developed by these 5-6 people, Ron Citron, Ferrante, Brosen, Wegman, and it's a wonderful paper if you go through it. I will probably share it. Okay. So what is static single assignment means? SSA, static single assignment. The meaning is when you write a program, you assign a variable only once in your program. Your hands are tied. You cannot assign the same same variable twice. In program text, why I will come to that? Because this single assignment could be inside a loop. I can say while x is less than 50, y1 equal to 20 or y1 equal to y1 plus 1. Okay, only one assignment, but execution time it will go around in 20 times or something like that. Okay, so it can be assigned multiple times if program is executed, but you are going to write it only once. So this is another intermediate representation. It looks very similar to 3 address code. Okay, but it's really not, because it has more restrictions. It is what is called a sparse representation, because unlike 3 address code where a definition you have to trace where is it being used, here you can directly associate with use site, because variable is assigned only once. So wherever it is used, you know that this is the variable. Okay, unlike a definition. So look at these 2 programs. So I have some if x equal to something else, x equal to something else, another if, let's say this is y is greater than 10, and again y is greater than 10, z equal to x plus 1, else w equal to x plus 2. Okay, just by looking at this program, it is very difficult to tell which definition of x is reaching here, which definition of x is reaching here. Okay, it could be this definition, it could be this definition, there might be some other definitions, because this is a regular program. You have to do analysis. On the other hand, I say that, oh, you cannot assign x more than once in your program. So let's say this is x1, this is x2, this is x2, this is x1. Now if I ask for this x1, what is the definition? There is only one definition. You don't even have to kind of look at it. You just say, oh, wherever x1 is defined, that is the definition. Directly associated with the use. Okay. This is why it is called a sparse representation. You don't have to create very dense graphs for definition and use. What is the advantage of such a representation? What can you think of before I show you? Suppose I give a program where I tell you that okay, no variable is assigned more than once. Traceability becomes easier. Okay. What did you do with available expression analysis? You had to find x star y is an expression, whether it is available or not. So what were you supposed to do there? Where variable is getting reassigned. You have to worry about gen, you have to worry about kill. Now suppose you are told that there can be only one assignment to x, only one assignment to y. What can you do then? There is no kill. Excuse me, sorry. Right? With such an assignment, such a restriction, there is only one assignment to x. How can it be killed? If x star y is there, it has to be the same expression. Okay. So you can directly access points where relevant data flow information is available. Because assignments are the most challenging thing in a data flow analysis. That's where information changes. Okay. So let's look at SSAIR. So in SSA form, every variable has exactly one definition. A use of variable as a corollary is reached by exactly one definition. But control flow is like traditional program. Okay, only thing is variable will be defined only once. So this creates a problem when, so you have to convert a regular program into SSA form. I think I should have said that. So when you are converting, in your original program there are multiple assignments like here. Okay. So there is some magic needed to create SSA form. SSA form, I mean, I cannot ask programmer to restrict himself or herself. Programmer will still write in C or Python or whatever language. I have to convert that program which has multiple assignment to a variable into a form which only allows single assignment to a variable. So I need some magic. Okay. So here is a simple program, very simple linear program. Variables of interest are only shown. Can you convert it to SSA form? And to do that, you don't have to create new variable, you create version numbers like I1, I2, I3, J1, J2, J3. Can you do that? All of you, please. Again, do it intuitively and make sure when you execute the program, the result should be the same. You cannot change meaning. Otherwise, I will just delete all the assignments. So what are the problem? Why is it not in SSA form? I is assigned 2 times. J is assigned only once. So which means you need 2 copies or 2 versions of I. What will you do? I and I1, I1, I2. Okay, fine. So have you changed it? Done? Done all of you? So let me also do it. This is easy. So I1 is 0. Did you make this change? Then I2 becomes I1 plus 1. Please check. It is important, otherwise your program will give wrong answer. And then J1 becomes I2 times 5. J1 can no longer use I1. Okay? Easy? Now change this program. What are the problems? Both I and J have 2 assignments. I has 2 assignments, J has 2 assignments. Let's do it and have our break, is it? Yeah, after this we'll take a break, and after coming from the break, I will solve it. How long is the tea break? Half an hour, very long. So we can discuss it over that, whatever challenges you face in converting this, okay? And if you can't solve anything, some challenge, just write magic. So got it? Any challenge you face to convert this into SSA form, just write magic. and then solve it. Later we'll see how to do the magic actually. And tell me how many times you need magic.